Welcome back. So this is our new recitation. So in this recitation, okay, maybe first of all, if you remember, last time we discussed, the power series and Taylor series. Actually, today we will have one more question about power series. Last time we didn't solve a question like this, so I think it's a good place to revisit power series. Okay, here, and also new topic will be actually the applications. Okay, applications of Taylor and Maclaurin series. Okay, fine. So the first problem is the following. So we try to find, maybe we should have done this problem in the last lecture, but anyway, so let's do this now. So let's try to find the radius and the interval of convergence for the given um, power series. So remember, this is not that much hard. We first start with the defining sequence. So let me define a sequence here, right? This is your sequence. Oops. Okay, n. Oh, n. So is that right? Okay, fine. So something like this. So this is an. Okay, then what we are going to do, we just apply, apply the ratio test for uh, for for this thing. Okay, so let's apply. So limit n approaches to infinity. So we should look at the following expression, the following ratio, right? So just look at this ratio. So let's see. Let's try to analyze. It's not that much hard. Now, okay. So what is it? So again, these things getting disappearing. Okay. Okay. Anyway, so n plus one, 2x plus one. Oops, is this minus one, right? So sorry, this is minus. So this is minus. Please correct this if you are taking notes. And okay, something like this. And times, so of course, 4 to the n, just something like this. It's not that much hard to see, but we have absolute value, of course. And we have cancellations, right? So this term and that one, they cancel out each other. But at the end of the day, we have a limit like this. So let me write it down. So n plus 1 and 4 to the n. Oops, no. Oops, 4n, right? And absolute value 2x minus 1, right? So of course, one term cancel here, this one, and we are done. So when, if you look at the limit will be just 1 over 2, absolute value x minus 1 over 2. Okay, take the parenthesis of 2, 2 and 4 cancel out each other. We have simplification as n approached infinity. This will be the result. Fine. And we know that, so the series itself, so this given one, this thing is absolutely convergent. This is absolutely convergent. Okay, this is absolutely convergent if, remember the condition, if this ratio, this thing, so we already compute the limit, the resulting term, if the resulting term is less than 1. If the resulting terms after this limit of this quotient, if we end up with a kind of a term like this here, and if the resulting term is less than 1, then we know that the given series is absolutely convergent. Okay, and therefore let's try to organize the expression here, and just note that if you have something like this, it means that of course easy algebraic manipulation. Okay, we have this for sure, no problem. And if you do one more step, we have something like this, right? X 5/2. Okay, fine. And actually, what does it mean? This means the following. So the first observation, we already observe the radius of convergence, right? So which is this number 2, right? And therefore, the radius of convergence, the radius of convergence, which is r is just, okay, 2. Okay, exactly the same number here, right? The highlighted number. And fine, so we have the radius of convergence, and we need to determine now the radius of, we have the radius of convergence, but now we need to find the interval of convergence. But we already know, because of the observation above here, we already know that this series converges absolutely on this interval, right? Minus this and 5/2. Okay, this interval. We already know this thing by theorem. And okay, fine, but this is not the whole story. Since it is absolutely convergent, this is convergent. And maybe I should write it down. So it converges, right? It's so for sure we have a convergence behavior on this open interval, but we need to be careful. We need to be careful. We need to check the endpoints. Maybe we may have convergence behaviors on the endpoints. So we also need to check the endpoints. Okay, let's check. So for instance, at x equals, so what is it? So at x equals left endpoint, for instance, this one. If you look at this, we have the following series, right? So what is it? So let me write it down. Just substitute x equals minus 3/2. Actually, you will directly have something like this, I guess, right? 4 to the n, and these are cancel out each other, and we have n here. So these are cancel out each other. So what we have, -1, okay, n, but we know that which is divergent. Divergent by n-term test. N-term test, if you like. So we have a divergence behavior at least one endpoint. So the other one, when x equals, okay, 5/2, okay, 5/2, and so if you substitute x equals 5/2, you will get a series like this, okay, this one, but which is also divergent, by nth term test. So we are done. So which means that no worries for the endpoints, right? So there is not that much new information coming from endpoints. Therefore, so the interval of convergence, let me call it I, will be this interval. Nothing new, but we always need to check the endpoints. Maybe some other question, one of the endpoints may be included in your intervals. Okay, you need to check the endpoints, because the theory in the first place tells you only the absolutely convergence for the interior points. Okay, and therefore you have a convergence behavior for the interior points and endpoints. You need to check endpoints um, also. Okay. Uh, Fine. So this is the first problem. So let's see what we have. Okay, first problem is done. And the next one. Next one is about, okay, now here is the application part. Now we will use Taylor or Maclaurin series for certain applications. For instance, try to estimate the following number here. So the first one is an exercise, a nice exercise. There is an example in your lectures, actually, check this. And we will try to estimate this number, of course, with some error. There must be a kind of error, of course. And let's see. Okay, remember why we use Taylor and Maclaurin series, because these are just polynomials. Okay, maybe you have infinitely many terms, but you may stop somewhere, right? You can take finitely many terms. At least these are polynomials. It's easy to calculate. Therefore, they can be used to estimate the values of complicated functions. This is how basically your calculators do their job, basically. I mean, they use these kind of algorithms. Try to estimate a value of a function by using polynomials or by just computing the value by using polynomials. So this is the idea. This is why we use those series. Okay, fine. First, we need some information about, so here is the idea. So we need to find a power series, or if you like, Maclaurin or Taylor series, Taylor series representation for ln 1.1. Of course, we first for the function, then we will evaluate the value. And so let's see. So what was the algorithm? If you remember, we start with what we know. We start with, for instance, this one, our old friend, right? 1 over 1 minus x. Let us start with the series, okay, x to the n, and starting from 0, but we should be careful. This is the case if absolute value of x is less than 1. So we start with this very well known. So we know the behaviors, we know the radius of convergence, we know the interval of convergence, we know everything about this series. So let's start with manipulating this series to reach what we need. So let's see, what is the first move? Just replace x by minus x. Okay, so if you do this, so you have 1 over 1 plus x, then of course, and starting from 0, minus 1 to the n, new expression, x to the n, of course, we still have the same interval of convergence. And it's not enough. We need something related to logarithm, right? Remember what kind of tools we have, integrating and differentiation. Then we can integrate and integrate both sides with respect to x. Okay, so if you do this, then you have ln 1 plus x on the left-hand side, and on the right-hand side, you have, remember, term-by-term integration. And fine, let's do this. Minus 1 to the n, x to the n plus 1 divided by n plus 1. Okay, is that correct? Remember, we did this before. We have more or less, we have the same kind of interval of convergence. Fine, so we are done actually. This is our expression. Now just put x equals 0.1. So if you do this, ln 1.1 will be, since of course this is less than 1, we can use it. So On the left hand side, of course you can substitute. On the right hand side, you can substitute, but we don't know the equality here. But equality holds. Why? Because 0.1 is less than 1. This value is in your interval of convergence. Therefore, you can use this equality. Otherwise, it's not always true. For instance, for x equals 2, you cannot say that left-hand side and right-hand side are equal. No. Okay. Since we are in the radius of convergence, we are done. I mean, this is n0 minus 1 to the, okay, n plus 1 here. What else we have? Times 1 over 10 to the n plus 1. This is your expression now. So let me call it, so this is our important observation. Now we have a kind of a series representation for this value on the left-hand side. We will use it. Remember, this is on the right-hand side, you have an alternating series, right? So this is, and so on the right-hand side, so remark here, right-hand side is an alternating series, which is convergent, So you have a convergent alternating series. You can easily check, for instance, by using alternating series test. You have alternating series. Fine. Now let's apply. So we need a kind of estimation. Remember, we have a nice theory for to estimate alternating series. So just apply the error estimate theorem for the alternating series. On the right hand side. What? Okay, I don't know. So I have some technical problems. Why these are disappearing? I don't know. But we have an alternating series on the right hand side, right? So okay, fine. So let me call this term an. Let me call it an, and just observe that. So this theorem tells us that the sum. So how can we apply this thing? So the sum, let me call it S. This is the number we wish to estimate. Can be approximated by the partial sum. Let me denote by SK, but partial sum of the first, so this is important, the first k terms of the series, with, remember the error was, I mean our theorem, make sure that the error we are looking for is less than and equal to the first omitted term. So let's analyze. So first omitted term. And just observe that, so S will be approximated by SK, right? So what is SK? By definition, first sum of first k terms. But be careful. Be careful if you look at carefully here. Here, so where is it? Maybe I should specify here. Look at here. N starts from 0. So therefore, you should be careful a little bit. So what is the deal? So therefore, the first term is A0 plus A1 plus A2. Dot, dot, dot. It goes like this. What was the final term? If you have a K term, K minus 1, right? So this is exactly, now you have K many terms. Be careful. Therefore, the first omitted term here is not k plus 1. The first omitted term is actually ak. This is the first omitted term. The first omitted term. And so, with this observation, we need to be careful. So let's see what we have. Therefore, now this was our first step. So we apply this. So let's try to find. So remember, we need to find enough number of terms such that the error is less than 5 times 10 to the minus 4. We want this. And by using this theory, I mean this first omitted term business, so let's see what we have. Just look at the following. Just look at. What was the first omitted term? AK. This is your first omitted term. If you compute by using our series, okay, we have k plus 1 and 10 to the k plus 1. And we want this thing is less than 5 times 10 to the minus 4. But this is exactly by using just changing the places. We have this 2000 less than 10 to the k plus 1 times k plus 1. Okay? We just, cross product, right? Fine, that's all. So if you look at carefully, so it is enough to take what? K equals what? How can you ensure this inequality? By just taking, it is enough to take 2 terms. Right? If you take 2 terms, it's enough. You have this error sensitivity, error accuracy, if you just take only this number of terms. Or if you take more terms, of course, you are in the still range. But I mean, this is not the question. Of course, you can take 1 million terms, but it doesn't much make sense. We try to make this procedure as efficient as possible. And therefore, we try to find the minimum number of terms, manageable number of terms. Therefore, it's enough to take k equals 2. So what does it mean? That means the sum, the sum can be approximated by using first 2 terms. Of course, we really wish error to be in this range. Okay, so that means that, remember, on the left-hand side, we have this number. Now we approximate this number by just using S2. S2 means the sum of first 2 terms. And first term is A0 and the second term is A1, and that's all. And just, it's enough to compute these two, I mean, this value, if you really insist this kind of error sensitivity. And if you compute, this is the first number, this is the second number, and if you compute it, of course, you have this kind of number. Okay, so the final result is ln 1.1, approximately this number, of course, with this sensitivity, with this error. 5 times 10 to the minus 4. Okay, now this is our result. Okay, fine. Okay, next one. So let's see. Let's try to understand this problem. So this is another application. For instance, you may have certain integrals that actually you may not compute it exactly by using elementary methods. Okay, but still we can approximate the resulting value of this integration. Again, by using the same idea, using polynomials. So in this question, if you look at carefully, you cannot solve the integral exactly, right? In part A, I mean, by using elementary methods. But this is basically what computers do, actually try to approximate the value of integral by using certain series representations. Okay, so let's try to understand what's going on. So part A. In part A, as before, we start with so we wish to um, we wish to find a series representation. Okay, maybe I'm not going to write this. We wish to find the series representation of the integral above. So let's start with, as before, start with the very well-known series representation, which is this. As you see, our starting points are very standard. Either we start with this series or some other very well-known ones. For instance, the series of sine function, cosine, maybe natural exponential function. We use something we already know. Okay, this is our starting point. So let's start and modify it as follows. So first step, as before, somehow we need arctangent, right? Therefore, just start with replace x by minus x squared. So why these things are disappearing? I have no idea. Maybe I'm just touching somewhere wrong. I don't know. Okay, anyway, so let's start with this. So on the left-hand side, we have this expression, and on the right-hand side, n starts from 0 because of this minus. We have new expression here, and x to the 2n. And we have exactly the same. If you compute, just replace x by minus x squared, we have the same kind of interval of convergence. So more or less, it looks familiar if you integrate. And then integrate both sides. Integrate both sides with respect to x, of course. If you integrate on the right-hand side, now you have arctangent x. And on the right-hand side, if you integrate minus 1 to the n, okay, x to the 2n plus 1 divided by 2n plus 1. Okay, so we have similar thing here. And we almost done. Remember, we need something x to the 4 inside, and we have something x squared in front of this arctangent. And let's do it. And just replace x by x to the 4, and then multiply both sides by x squared. So let's do this. So first do the former replacement. Instead of x, we have x to the 4. On the right-hand side, we have n0 minus 1 to the n. If we have x to the 4, 8n plus 4, I guess, and divided by 2n plus 1. Still, if you do the calculations, we have the same thing here. But this is not enough. Actually, we multiply both sides by x squared. So let me do this. And therefore, we have, instead of 4 here, with the new power, we have 6 here because we multiply both sides by x squared. And we are done. Actually, we have what we need. We have the integrand, right? If you look at carefully, we have the integrand, the expression inside the integral. And we have this. But now we need to integrate. But let's do this. And now take the integral, right? The definite integral. So let me write it that way. So if you do this, so we have 0 to t. Now we have this integrand, so arc tangent x to the 4. And on the right-hand side, term by term integration. And then, okay, maybe, okay, I just skip the intermediate steps. If you do the integration and compute the definite integral, now we have a definite integral. You have t to the, okay, something like this, divided by this term, right? This is from the integration, and this is your other term, okay? And we evaluate it from 0 to t. When you substitute t, we have this expression. When you substitute 0, we have nothing. Okay, fine, that's all. And of course, maybe we should be careful here. Now t should be less than 1. Okay. Now we have a parameter t. Okay, fine. That's all. We have the expression. This is it. This is how we have basically. This is our. Oops. Okay. Okay, fine. Okay. This is what we need. Let's use it. Now, in the second part of the problem, remember, so what was it? Let me show you. In the first part of the problem, remember, we really want to estimate when t equals 1/3. And actually, this can be done because we know that this series representation can be used with this restriction. Therefore, since t is 1/3, we can use it. We have this equality. Therefore, let's use it. So part B. So from part A, so use part A. I mean, the resulting thing, I mean, this part, if you like, this final picture with t equals 1/3. And then we get the following. So, so we want this expression to be approximated, right? This is what we want. So arc tangent x to the 4 dx. Oops, we have somewhere here kind of a dx. But of course, these are disappearing again. Okay, it's really weird. I don't know, so I will correct this later, okay, sorry. In the final notes, they will be corrected. Okay. Okay, fine. So let's see what we have. So on the right-hand side, so I just forget what we have. Okay, I guess. So remember, we have t to the power 8n plus 6 minus 1 to the n and summation. Six or 7, I guess, right? Okay, anyway, so let me move on. So on the right-hand side here, so we have n from 0, just substitute t equals 1/3. We have something like this. So let me write it down directly. 1 over 3 to the power, okay, 8n plus 7. is it? So we have 8n plus 7. Okay, that's all, I guess. So let me denote this term, the everything denoted by, let's say, an. Okay, an. So let me use, I mean, on the right-hand side, we have, of course, an alternating series. So the right-hand side is an convergent alternating series. Okay, and therefore by the error estimation theorem, remember, by error estimation theorem, let's see what we have. By error estimation theorem, S, the sum, the resulting number, can be approximated, right, by the partial sum, let's say Sk. This is the, as before, we start with A0, A1, dot, 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 a k minus 1, we have k many terms here, k terms. So we have this partial sum of the first k terms. Okay, and with remember, with the error less than, maybe I should write it down, not here, but here, with the error, remember, error less than and equal to first omitted term. But here, as before, what is the first omitted term? So what is it? So the first omitted term is AK. Remember the AK here, this indices basically ends k minus 1, and therefore the next term will be AK. So AK is the first omitted term, and if you compute this, it's not that much hard. We know what is AN. So we have this times, okay, 8k plus 7. Okay, times one more term, 8k plus 7. Okay. And what we want. So let me write you what we want. We want actually the error, remember, error less than 10 to the minus 6. This is what we want. And actually, this is not that much hard. As you see, this expression, let me write it down. This term, okay, times, so what was it? 1, okay, 2k plus 1 times 3, okay, 8k plus 7 is less than 10 to the minus 6. And this is the case if and only if, okay, let me collect the terms. I mean, okay, this times 2k plus 1, 3, 8k plus 7. This should be greater than 10 to the 6. And of course, it's a huge number, but if you look at carefully, enough to take k to be 1. Enough to take k to be 1. So what does it mean? One term is enough. Actually, therefore, this integral 1/3 x squared arc tangent x to the 4 dx can be approximated. It's enough to use S1. And S1 is just only the sum of first term, which means this is just the first term. And the first term, if you compute when n equals 0, 7 times 3 to the 7. With, of course, with the following sensitivity. Error less than 10 to the minus 6. Okay, fine. So this is our result, basically. This is how we, as you see, we have something bad. We cannot integrate it, but still by using, remember, this is an approximation here. This is not the exact value, but with this range here, we can really approximate. Okay, these are disappearing. Okay, maybe we should stop here. Let's take a break. And then the next time we will continue with further applications. Okay, let me stop here.